will be ready to go when the projector lights up. Here it comes. Okay. I believe we were on this slide when we ran out of time last time. Okay. Oh, yes.
Have you created a test?
I'm sorry?
Test.
Test today? No.
Have you created?
No. I think I just explained that I'm behind in grading because every moment I've had in my office that I haven't been advising somebody or dealing with somebody, I've been working on spring and summer schedules. And I'm hoping to get some of the grading caught up this weekend, but I've got that much grading to do. I don't think I'll get it all done Friday, because once they give me the Benadryl, I've got maybe 15 to 30 minutes, and then I'm out, okay? So I won't be grading any after that. And hopefully I'll have some time to get going before that. Okay. Any questions? All right. I did think of one other thing just before, but now it flew the coop. Okay. Oh yeah, what we're going to be doing today. Today we have class until 5:45, and then we have a lab from 5:45 to 7:45. I don't think it will take you the full 2 hours to do it. It shouldn't. And this time we're not in the same lab we were last time. We're across the hall in 252 because we needed longer lab table space, and those round or hexagonal tables just weren't big enough for what we're going to be doing today. So we'll be going to 252 just across the hall. If I'm not mistaken, the next lab we'll be doing down in 259 unless there's a class in there. So we'll go with that. All right, any questions before we get going today? All right, talking about force, okay? As I said before, I'm pretty sure I told you, simple definition of force, a push or a pull, okay? Capable of changing an object's state of motion, okay? The overall effect is determined by the vector sum of the forces. That's called the net force on an object. And here's the example given. It sort of follows the picture that's on page 33 in your text. This looks like an old ammunition ship, okay? It could be refrigerated stores. I don't know. No, it's not ammunition. The number's wrong for that. Could be refrigerated stores or some other type of cargo ship, okay? In the U.S. Navy. So they're not flying a flag, so I assume it's the U.S. Navy. They should be flying a flag. But anyway, they're coming in or leaving Port 1, and you see when they are, they've got tugs pushing on them. And that's what this is talking about here. And they even drew the ship to look somewhat like this. Okay? Now, if the two tugs are pushing like they show in the text there, in that picture, both of them pushing on the starboard side of the ship, okay, then, and each of them pushing with 1,000 units of force, then the total force acting on it is 2,000 units to the east. Okay, I don't know why they picked that as east, but that'll be east. If these two are pushing 1,000 units each to the east, you add the vectors just like you would normal numbers, 2,000 units to the east. However, if one of the tugs got his information wrong, and one's pushing on this side and one's pushing on that side, and neither one of them can figure out why they're not having an effect on the ship, it's because the vector addition goes to zero. Even though they're both pushing with 1,000 units of force, because these are vector quantities, if the directions are opposite, the net force is zero. Here the net force is 2,000. Now, if you happen to have the little tug on this side pushing with 1,000 units of force to the east, but on the other side where you can't see, there's a bigger tug pushing with 2,000 units to the west. The little tug is saying, what is going on here? I'm going backwards even though I'm pushing to the east. And that's because the net force 1,000 to the east, 2,000 to the west. Net force would be 1,000 units to the west. Okay? So you add according to vector sums. Now, I don't know if it's any better, probably not, but it's maybe a somewhat more practical application. When we first moved into the house where we currently live, previous house we lived in hardly had a tree on the lot. It was a small lot, and we had a nice tree next door to us we got a little bit of shade from, and there was one in the back corner we got a little bit, but that wasn't a very nice tree or anything. We planted a few trees, didn't get very big by the time we moved, but when we moved to the current house, trees all over the lot. I mean, we both of us like that. Big old trees too, but also some scrubs. There were 2 pines that had sort of sprung up under the canopy of great big old oaks, and those were spindly, crooked, ugly-looking little pines, and they were trying to reach for the sun somewhere up there and just looked pretty bad. But the previous owner had left them there. I don't know how long, but they didn't look too good, so we wanted to take those down. So my father-in-law came down from Huntsville with his chainsaw. I didn't have one at that time. And my brother-in-law also came down from Huntsville, and they were going to help me take the trees down. Well, the house nearby, the trees were already leaning strangely. We didn't want the trees to fall where we didn't want them to, so they also brought some line, and we threw the line as far as we could up and caught a limb somewhere high in the tree, and came down, and then we pulled a stronger line up there, and so both my brother-in-law and I could get and pull on the tree while my father-in-law cut it, and that way we could get it to land where we wanted to. Now, the most efficient way for us to pull is if we pull, both of us pulling in the same direction. What would be wrong with that picture? It's a tall tree. Spindly. It's going to fall right on top of us. So therefore we chose to sort of make a wedge there. I pulled this way, he pulled that way. Okay? Now we lost some net force because, let me see if I can find some space to write. Okay, let me write here. Okay? Let me get my pen set up. Okay. If the tree was here, and I pulled this way, he pulled that way, then I have a component of my force in this direction, but also a component of the force in that direction. Remember, forces are vectors, and you deal with the components. He had a component of force. Let me do a different color. You want to choose a color? Anybody? Purple, okay. Dan will be purple. He pulled in that direction, so his component was here, but it also had a component in this direction. So we each were pulling down. So these two add, so the total net force would be in this direction. These two basically cancel each other out because mine was pulling this way, his that way. So we lost some net force, but sure enough, the tree fell in between. We both managed to lift the top of it. Okay? And so that's an example. Other examples, if you, we have, in fact, my in-laws had it, but they sold it to us. Long story, but place up in Winston County, and it's interesting to drive through there because the roads sort of go like this as they follow the ridges, kind of, and of course the power lines have to go like this too. And every time they make a bend, they have to have a guy wire over here, because otherwise, at a bend, the wires, the power lines are going to pull the pole and make it lean or pull it over, okay? So you have to have the guy wires on the back side to keep it up straight. And you've probably seen that. Notice that. That's because the net force on that pole needs to be zero. if there's a bend in the road and one's going this way, one's going that way, that's going to pull the pole over. Every time. No way to avoid it. So they put the guy wires behind to keep it net force being zero. So that's what we mean by net force. Okay? Whoa. We already did this slide, so let me go through it. All right. So that's what we mean by net force on the object. You add the forces vectorially, not adding the numbers, adding the vectors. Okay? We're not going to get that much in the vector addition, but just keep that in mind. Vectors add differently from just regular numbers. All right, moving on from that, there are four fundamental forces. This is on page 32, the right-hand column, last paragraph on the page. Four fundamental forces basically in nature. Now, I'm sure there are other forces, but these are nature's forces, not me pushing on the desk or pulling on a wagon or something like that. Those are forces, those are applied forces. These are the fundamental forces of nature, or at least four of them. Okay? Most basic of all the interactions, gravitational force. All of us are affected by gravity. That's why you're on the floor rather than up in the ceiling or walking on the wall. Okay. The gravitational force is always a mass interaction. Okay? It's governed by the masses of the objects. The mass that influences us is the Earth. Enormous mass. And that's what's pulling us down. But the Earth is a fairly small mass compared to that of, say, Jupiter. Enormously more massive than the Earth is. And even way more massive than that is our Sun. And here's Dimitri. Speaking of masses. Okay. There you are. Okay. Now, so all the motion of the planets around the sun governed by gravitational forces. Okay? The motion of the moon around the earth governed by gravitational forces. All the stars in our galaxy, the Milky Way galaxy, the movement of them governed by gravitational forces. And even the galaxies between each other governed by gravitational forces. Now, if you hadn't thought about it too deeply, you'll realize gravitational forces act over a very, very large range. Okay? But they're relatively weak forces. Overall, they're pretty weak, but they have a huge extent to them. Between galaxies, that's pretty big. Okay. Now, other gravitational forces, of course, keep us on the ground, but also keep all those satellites in place. You know, if you're using GPS, those are based on fixed satellites in place in orbit. If you're getting signals from a long way away, those signals to your cell phone or wherever, most of those local things are bouncing off stations within sight of each other. The longer distance basically are going to a satellite and coming back down. Like when you hear the news people talk to someone in Afghanistan, that's going to a satellite and coming back down. Communication satellites, all the satellites out there, their motions are governed by gravitational forces. All right, next kind, these are stronger forces, believe it or not, but they don't have as large an extent. Electromagnetic forces. The basic interaction there is not by mass, but by charge. Here's a fairly major difference between these. There's only one, so far as we know, quantity of mass, and that's the mass. However, how many charges are there? Two. There are either positive charges or negative charges. Now, somebody might say there's also neutral charges. Well, to me, that's not a charge. Okay, that's zero charge. So, charge interactions govern electromagnetic forces, especially the electric part of it. On the magnetic part of it, magnetism is governed by how many poles. two. We typically call them a north pole, a north-seeking pole, and a south-seeking pole, or something like that. So again, there's two opposite entities there, and that's the nature of the electromagnetic forces. Okay? Now, like I said, electromagnetic forces are stronger, really, believe it or not, than gravitational forces, but they don't act over as far a distance. Okay. One of the sort of classic examples of this, I don't know if you've ever noticed it, if you have a rubber comb, say, and you have enough hair to comb, which some of you do, but I don't. Okay, never mind that. And you comb with a rubber comb. Now, it needs to be a dry day, and your hair needs to be relatively clean and not very oily, nothing you put on your hair. And you comb it with a rubber comb, hard rubber comb. And I don't know if you've ever noticed, sometimes when the comb leaves your hair, the hair sort of tends to follow it. Not that it's tangled, it just tends to follow it. And you can take that same rubber comb, if you have little strips of paper on the desk, you can actually pick up the pieces of paper with that. Why? When you're combing your hair with a hard rubber comb, you're basically knocking electrons off your hair onto the comb. So your comb gets net negatively charged, your hair is net positively charged, and that's why the hair tends to follow the comb. Now, on a damp day like today, probably not going to work, okay? Because the moisture in the air helps conduct the charges back to where they belong, okay? But on a dry day, your hair is fairly clean, not oily or not got any kind of spray or anything on it, it will sometimes work. Now, the reason it picks up the little pieces of paper is because it's negatively charged. They're neutral charge, so they get attracted to it, okay? Like I said, that's not a charge, but they're not negative, so they get attracted to it. Now, why do we say that's stronger than gravitational? Because they will pick up the little pieces of paper. Gravity is trying to hold that piece of paper on the desk. The electrostatic force actually lifts it off the desk. So it's actually, in that short range, stronger than gravity. Hold it up here, gravity wins. Get down there, the electromagnetic charge. On close proximity, electromagnetic forces are strong. Now, not just combing your hair and picking up pieces of paper, all your atoms, molecules, all of chemistry, and much of physics deals with electromagnetic forces. In fact, the lights are electromagnetic forces. Anything, energy coming from the sun, electromagnetic forces. Of course, the electricity in your devices, electromagnetic forces, they're all over the place. Okay? And what makes molecules, what compounds, electromagnetic forces. Now, these next two have very creative titles. A weak force and a strong force. These are nuclear forces. Okay? And when it says a weak force, it's much stronger than gravity or electromagnetic forces, but it's weak compared to the strong force. Pretty nebulous naming, wouldn't you say? Okay? Here's Justin. Good deal. Okay. These are involved in certain nuclear reactions. Okay? That's all they say about it, so we'll leave it along there. The strong forces, let's think about this. I think we've already mentioned all of the positive charges in an atom are concentrated in that tiny little nucleus. Okay? Incredibly tiny nucleus, but very massive compared to its size. In other words, incredibly dense. Okay? So all the protons, the positive charges, are crammed in there. The electrons are out here floating around in space around that very complex condensed nucleus. Okay? Now, one of the rules of electromagnetic forces are, what do like charges do? Repel each other. Unlike charges attract each other. the comb picking up the pieces of paper. Unlike charges, even though one's just neutral, it picks it up. Okay? So wait a minute. How in the world can all these positive charges get crammed into a tiny, incredibly tiny little nucleus? Why aren't they repelling each other like crazy? Because of the strong nuclear force. Much, much stronger than the electromagnetic force, and stronger than the weak nuclear forces. Those are the strongest forces, as far as I know, that we know of. Okay? Incredibly strong forces. Okay? Holding those nuclei together. Okay. Now, all right. And by the way, the stronger the forces, the smaller the range. Okay, that's pretty incredible. Those strong nuclear forces, their range is only about the diameter of a nucleus, which is incredibly small. But within that, they're incredibly strong. Okay, so going like that. Now we get back to motion. Okay, that was a little outtake for just to get enough talked about forces so we can talk about motion. Then after we talk about motion, we'll come back to forces again. Okay, sort of ping pong here, going back and forth. All right. Remember Aristotle versus Galileo. The natural motion question that Aristotle posed. He said, natural motion on the surface of the planet requires a constant force to keep it moving. That was his statement. Galileo pretty much disproved that and said, no, it's not necessary. No, in the absence of unbalanced retarding forces, the motion will continue. Okay? Now, we know that in reality, there are never, or hardly ever, any complete absence of unbalanced retarding forces. Okay? We'll talk about that in just a second. So here we have a ball rolling on a nice level floor. Okay? Now, if you just roll the ball with no additional force after it leaves your hand, and there wouldn't be, then it's running into, and by the way, the ball's rolling this way. I'm acting this way. The ball is rolling this way. But there's always air it's pushing against. Wait a minute. Does air have resistance? Air is air. Is there any resistance to air? Okay. I can remember when I was a young child and we were driving on trips somewhere. Could be just to the store or something like that. We lived way out in the country, so we had a ways to drive. We never had an air-conditioned vehicle until I was probably, I'd say, high school or college. Okay, my dad was too cheap, and back then that was an expensive add-on. Okay, it wasn't standard with the car, so we never had one. So we always had the windows down in the summertime, or spring or fall. Okay, the windows were always down, and I just enjoyed like crazy sticking my hand out the window. You know, get your hand in the window. Yeah, I'd hear all the time. But if I could get away with it, I'd stick my hand out the window. Because when you're going at a slow speed, yeah, not much there. If you're going at a fast speed, it almost feels like it's going to take my arm off. Why? Because air has resistance. It's just that the higher velocity, it's greater and greater resistance. Does air have resistance? If it didn't, skydivers wouldn't operate. Okay? A parachute would not work. Parachute just gives more place, more surface area for the air resistance to slow you down. Thank goodness. Otherwise, they'd be in serious trouble. I'm not about to jump out of the plane. Okay. So there's always some air resistance. There's always also some floor resistance. If I roll the ball across the floor, you think I can do that quietly? Probably not. You're going to hear it. What is hearing? What is making the noise? Things bopping into each other, because otherwise there wouldn't be a sound if there wasn't a compression caused by some sort of friction with the floor. So you have floor friction and air friction retarding the motion of this ball in this way. So what's going to happen? The ball will eventually stop, because once it leaves your hand, there's no more force being added to it this way. All the forces are opposing it. And frictional forces always oppose motion. Frictional forces never increase motion. They always retard motion. Okay? Now, so let's think of a bowling alley. What do they do to those floors on the bowling alley? They are waxed as slick and smooth as they can possibly be. So when you roll the ball, even though you're still hearing it roll down the thing, hopefully, and you don't want to bounce the ball down there, but it's going to have at least amount of floor resistance. There's always going to be air resistance, though. And so, fortunately, you roll it fast enough, it'll have enough energy, hopefully, to get to the end. Okay. Now, if you have a constantly applied force in this direction, that adds up to the net forces on the resistances, then your net force is zero. Now, if the ball is rolling and the net force is zero, what's going to happen to the motion of the ball? Does that mean the ball stops? It means it doesn't accelerate, but it continues in its state of motion. The ball now moves at a constant velocity. With the net force in that direction, the ball's got to stop at some point. With the net force being zero, if it's coming this way, it keeps coming that way at a constant velocity and would never stop, okay, unless it hit something that made it stop, okay? So a net force of zero does not mean zero motion. It means zero change of motion. Now, if it was at rest, it stays at rest. But if it was moving, it continues moving until something makes it stop. Okay? So, in the absence of an unbalanced retarding force, and you see these are unbalanced, so the ball will stop. There's nothing in this direction. These are now balanced. These two add to be the same quantity as this. The vector sum is zero, so the ball will keep moving at whatever velocity it was moving. It maintains that until something makes it stop, or speed up, or change direction. Okay. Now, the characteristic of a material that measures the object's tendency to resist the changes in its motion, even including rest motion, that's called inertia. That's a long definition for a simple word. The measure of an object's tendency to resist changes in its motion. So let's say I have a ping pong ball here. I throw it as hard as I can at your sink, okay? Is it likely to hurt? Is it likely to hurt?
Yeah.
You think so? A ping pong ball from this distance? It's not even going to get to you. Well, never mind. Say again? I'm sorry. Oh, yeah, it might. If there's any wind in here, it might do that. Certainly going to curve down. Yeah, there's wind coming in there. Okay. But if I had a bowling ball that I could throw at the same as hard as I could, if I could get it there, that might be a different story. Why? The bowling ball has a lot more inertia than the ping pong ball because it's more massive. So inertia is related to mass. Okay? Same kind of concept. Drop a ping pong ball on my foot. Not going to pull my foot back. Not going to hurt. Drop a bowling ball. I'm going to move the foot if possible before it lands. Okay. On the other hand, what if that ping pong ball was at rest? What if I go to kick the ping pong ball? I'm probably not even going to notice that I've made impact with it. I'd hear something maybe, I wouldn't feel much. But if I go to kick a bowling ball, per foot. Okay, bowling ball may not feel much, but my foot feels it big time. So even changes in motion, even if it's at rest, that resistance to change of motion, that's called inertia. Okay. So let's go back to this idea of balanced and unbalanced forces. Okay? Now, as I said, most of the time, you always have some type of retarding force. If nothing else, it's going to be air resistance. Okay? The only way you can get out of that is to get out into outer space. In outer space, no air. So no air resistance. If you're far enough out there, not even any gravitational force to speak of. So that's where we usually talk about if you have no unbalanced forces. That's not the only place, but it certainly could be. Natural motion in free space is constant velocity. Okay, constant velocity. That means no additional force is being made, so the thing just keeps moving forever. Now, free space means far enough away from objects so your gravitational force is negligible, and the assumption is absolutely no air out there, so there's no air resistance. So motion continues unchanged when there's no unbalanced forces. No air resistance, no friction, nothing. Okay? No gravity, nothing. Okay. Now, if you have a retarding force, what would happen to this? Okay, here's a picture of that. Let's say that you fire a retro rocket. Okay? So the object is moving this way, you have a retarding force this way. Maybe you fire a rocket whose nozzles are facing that way. That is going to slow down that natural constant velocity. Change of velocity. If your retarding force decreases the speed, it's in the opposite direction of the motion. Okay? If, however, your nozzles are facing this way and you fire off a rocket, then that's going to increase your speed. Boost is needed to increase the speed. Not going to increase unless you do something to make it increase. Not going to decrease unless you do something to make it decrease. But what would happen if the force was, say, perpendicular to this? What's that going to do to the object? Say again? Yes, that's going to turn it. That's going to change its direction. But remember, a change of direction is also a change of velocity. Okay? Speeding up is a change of velocity. Slowing down is a change of velocity. But changing direction is also a change of velocity, because velocity is a vector quantity. And when you do have a perpendicular force, or any force with a perpendicular component, you're going to change the direction of that object. Okay? And this is out in free space where you have nothing else that's retarding, just these unbalanced forces that you're applying to it. Okay? So a retarding force decreases the speed, boost increases the speed, a sideways force changes its direction. May or may not change speed some, but it will change its direction. Does that make sense? Now, okay. That's all they've got slide set, and basically in the text as well, on pictures of that. There is sort of a dumb mistakes and misunderstandings at the top of page 35. I'll let you read that and do whatever you want to with it. I've heard that discussed a lot, and this discussion isn't particularly new or impressive. Now, what we have here is a time-delayed photograph, you might say. What you have is a jet black, perfectly dark room. Absolutely nothing in sight. And something's up here at the top holding a pool ball. Okay? Now, I don't know what device they have to do that. Maybe suction or something else like that. Is holding it there. fixed in place. Okay? You have a camera over here, perfectly black room, totally black room, and the camera has its aperture wide open, but there's nothing for it to record because there's no light in the room. Okay? And what you are going to do is start a strobe light. I believe it's once every 100th of a second or something like that. Maybe it's a 10th of a second. That's going to strobe at the instant that you turn off whatever's holding that pool ball in place. So what's going to happen is going to fall. But the time interval is the same between each of those things. That's the same ball. It's not different balls. One ball falling down, the strobe light is what's doing it, and the camera is capturing the ball every time the strobe comes on. Okay? What do you notice about the motion there? It falls a very small distance, that first 10th or 100th of a second, maybe a little bit further than the next one, a little bit more than the next one, then more and more and more and more. So it's increasing its speed as it goes down, right? Of course it is. Why? Say again? Gravity is pulling it downward. There's a net force acting on that ball, an unbalanced force. So therefore the ball is changing velocity as it falls. Okay? Now, Aristotle would have said that ball falls at a constant rate. Okay? It isn't. Slower up there than it is down here. Galileo showed that indeed the effect due to gravity is going to increase the speed. You have to have some force that changes the motion of the ball. And that force is the gravitational force. Now, at some point, if this was high enough, way, way, way up there, and you drop the ball, at some point the ball will fall at a constant speed. Okay? We call that the terminal velocity of the ball. Okay? As we saw the other day when I held up two pieces of paper, same mass, one of them was flat and one of them wadded up. When they were both flat, they fell at about the same rate. When I wadded the one, it fell much more quickly. Okay? Because of the air resistance. It had less air resistance than the flat one. Okay? Well, at some point, there's enough air resistance pushing up on the ball that balances the gravitational force pulling down, and then it reaches a constant velocity and falls. That's what Aristotle was observing when he said objects of the same mass, the rate of fall depends on the weight of the object. Well, that's because the gravitational force depends on the weight as well, and a light object will reach its terminal velocity much sooner than a heavier object will. So that's why he thought light objects fall slower than heavy objects. Okay. Again, ping pong ball, tennis balls. Okay. Now, here is a specialized formula that describes this motion. How far did it fall? The distance is 1/2 the acceleration. Anyone want to hazard a guess what the acceleration of that ball is? Acceleration due to gravity. Okay? That's the only net force acting on the ball. Okay? We're ignoring air resistance here. But this is a very specialized equation. And here's why it's specialized. We're measuring the distance from the top here, so the initial position is at position 0. Distance equals 0. Okay? Secondly, we're releasing this from rest, which means initial what is 0? Velocity or speed is 0. With those in place, this formula is perfectly correct. If those were not in place, let's say that the initial position was at some positive value or negative value, whatever, and then say you threw the ball upward or threw it downward, then your formula would look like this. I'm back in purple still. Let me get back to black. D is equal to 1/2 AT squared plus VIT, that's your initial velocity that you gave the ball, plus DI, whatever your initial position was. That is the complete formula that goes for any case. But if the initial position is 0 and initial velocity is 0, then this is the correct descriptor. Okay? Now, I don't know if the picture in the text shows the Leaning Tower of Pisa. Whether Galileo actually went up on top of that, he may have. He lived in Pisa. We know that. Okay? And when he was disproving Aristotle's theory that heavier objects fall faster than light objects, he went up to the top of the tower, supposedly, and dropped a heavy rock and a light rock. Definitely changes in masses, differences in weights, and they fell at the same rate. Okay? And that's what the picture here shows, according to the widespread story. Okay? Now, he did experiments. He didn't just say, hey, it makes sense that heavier objects fall faster than light. No, they don't necessarily. So what we're talking about here is what we call free fall. And here's the definition. Free fall considers only gravity, neglects air resistance. Now, if you have the ball high enough in the air, guess what? It's going to run into enough air resistance. The faster it goes, the more air resistance it meets. But as long as it's not falling very far, and it's a relatively massive ball without being a ping pong ball, then it will act in free fall. Okay. They have a little concepts applied, and basically it almost is describing what I did in class the other day. Now, they have a 5-step series of equations that they are dealing with here, and showing how they derive that formula from the basic thing, distance is equal to average speed times time. And if you want to work through those, they're certainly fine. The key is remember that formula, okay? That's the one. Now let's look at a few applications of that. Okay. Again, got a little ahead of myself here. With following objects, now, okay. Initially, we were talking about horizontal motion. They said on land, but any horizontal motion anywhere, okay? Now we're talking about vertical motion, and that's falling objects. And the definition for free fall, falling under the influence of gravity alone without substantive air resistance, with negligible air resistance. Okay. There's always some air resistance, but as long as you're not falling very far and your relatively massive object is falling, you can ignore the air resistance for most of the fall. Okay? Now, the distance is proportional to the time squared. That was the formula we just saw. That. The distance is proportional to the time squared. Constant proportionality, 1/2 the acceleration. And that acceleration is the acceleration due to gravity. Now let me say this too. I won't back it up, but I'll make this claim. Most of the time in physics, when the independent variable, time, or whatever the independent variable is raised to the second power, most of the time you're going to have a 2 in the denominator of the constant. Not always, but most of the time you will. And you can follow their little diagram there and explanation there, and they seem to indicate that the 2 comes from the average speed being the initial speed plus final speed divided by 2. And if you want to think that, that's perfectly fine. In reality, it comes from an integration constant. Okay? Now, I doubt if many of you have had enough calculus to know what I'm talking about there, But in reality, that's where it's coming from, an integration constant. So go with whatever you need to. Okay, so there's the first thing. Distance is proportional to the square of the time, not just the time. Now the speed increases linearly with time. Okay? And we knew that from our previous formula, the one they started with here. I'm going to write that one down too. Distance is equal to average speed times time. So you see from that, that's a direct proportionality without the time, time square. Velocity, average velocity times time. As time goes up, this goes up by the same amount. Here, as time goes up, this goes up by the square of that amount, not just by the amount. There it goes up proportionally. There your constant proportionality is your average speed. Okay? Now, here's something that's rather bizarre but true. The trajectories exhibit up and down symmetry. Does that make any sense at all to you? It may or may not, but let's go back to this picture here. How do you know I didn't throw the ball up from the ground somewhere below where the picture is and it just happened to stop here? Just barely touched it. You couldn't tell. The ball would follow the same pattern going up because as the ball is moving up, gravity is pulling down, slowing it down, slow it down, slow it down, slow it down until it stops, and then it falls down and follows the same pattern down again. Okay? That's what they mean by the trajectories exhibit up and down symmetries. Exactly the same type of motion. Okay? Now here is a really sick illustration of that. Okay? Because it's true. Have you ever seen these places on the news or somewhere like that, maybe even around where you might live or something, that when people go out celebrating, they fire a weapon into the air? Hopefully that's not done very much, but you see some of the other countries that seems to be a popular thing to do, just fire the weapons into the air. Here's the problem with that. If you were to fire a projectile into the air, give me approximately the bullet speed. Anyone know?
1,500 feet per
Second?
Like 1,500 feet per second.
1,500 feet per second. That's fast enough to do a lot of damage, right? That's why it's a bullet. 1,500 feet per second when you fire it into the air. Okay? The acceleration due to gravity is 32 feet per second squared. In other words, gravity is going to be slowing that projectile down at 32 feet per second each second. So it's at 1,500 feet per second on the way up, right? That means after 1 second is 1,500 minus 32. That's not much change, but then the next second up, that answer minus 32. The next second, that answer minus 32. So all the way up, that bullet is slowing down. And it's going pretty far up there, okay, because you're only subtracting off 32 feet per second every second. But at some point, way up there, it's going to slow down enough so it actually stops. But then what happens? Gravity is going to start pulling it down at 32 feet per second each second. So by the time it gets back down from however far it was up there, guess what its velocity is when it gets back here? 1,500 feet per second. Same as the muzzle velocity. Okay? So firing a weapon into the air, not a smart move, because somewhere that bullet's going to come back down at approximately the same speed you fired. Okay? Just hope nobody else is there. If you fired it straight into the air, you better move pretty quickly because it's coming straight back down. And if you're right there where you fired it, it could get you smacked in the head. Okay. Most of the time, we're not that good about firing perfectly straight up. Now, I kept having weasel words in there approximately. Because guess what? There's always air resistance. That will slow it down ever so slightly going up, maybe a little bit more so coming down. The reason I say ever so slightly going up is because if it was fired from a rifle, say, where the rifle,
So can air change its direction?
it can, if there's gust of wind, that certainly will change direction. Or even not a gust, just constant air in the same, that will definitely have some effect. Generally not a lot, because a bullet's a very small area. Now what I was saying about firing it into the air, if it's a bullet, bullets are very streamlined in the shape, right? And if it's fired from a rifle, and you tell me if pistols also have it. Do pistols have any rifling in the barrel?
Yeah.
They do. I thought they did. And what that means, it gives a little twist to it as it goes out, and that helps diminish the air resistance, okay? Because of the twisting motion, it goes more smoothly. That's at least on the way up. But on the way down, when it stopped, basically it doesn't have any twisting motion, it's probably going to tumble on the way down. And that's not as aerodynamic as going up. So there will be a slight reduction in velocity. Okay? So, up and down temperatures. Acceleration is the same for all objects. Same for a ping pong ball as for a bowling ball. Okay? Acceleration is the acceleration due to gravity alone. Now, sure, a ping pong ball is going to slow down faster because it reaches its terminal velocity faster, but that's a different issue. If you're talking about without air resistance, so, and actually, was it the first moonwalk, or a subsequent one? We landed on the moon a few times, and people have actually gone out and walked on the moon. But one of those times, one of the astronauts took up with him, it's a classic physics experiment, took a hammer and a feather up there. Now, what's true about being on the moon? No, there's gravity. The moon's not mass, a lot of mass, but no what? No air, no atmosphere on the moon. Took a hammer and a feather and dropped it. Landed at the same time. Because there is no air resistance on the moon. So sure enough, the acceleration is the same for all objects. The air resistance causes different objects to fall at different rates. But if they took my wadded piece of paper and a flat piece of paper and dropped them, they fall at the same rate. You know, a sheath of paper versus a single page of paper would drop at the same rate. Everything falls at the same rate if it's in free fall. No air resistance. Okay? And that's what that's based on. All right. There's that formula again. The distance that it falls is proportional to the square of the time. Whereas, and here's an example of that. Okay? If you go way up on a very tall building, don't do this. Okay? Because you don't know in the process who's going to walk under it. But if you were to drop an object from the top of the building, it's going to go 4.9 meters in the first second. No matter what the mass of the object is, no matter how heavy it is or light it is, generally speaking, it's going to fall 4.9 meters in that first second. But then look at this. It falls 19.6 meters in the second, after 2 seconds. That is no longer, that's not a linear fall. That's a quadratic fall, okay? Then 44 points. So you see this it's almost quadruples. Actually, it does quadruple. And then this one is 9 times this in 3 seconds. Okay? So you're going by the square of the time. And in 4 seconds, that's 16 times the distance that you were in the first second. Okay? Squaring are 4 times the distance you fell in 2 seconds, because this is twice as long. Okay? And you get this, and here's the first time they introduce it. In the SI system. What is the SI system? System International. And what is another sort of common name for that? The what? We usually call it the metric system. SI is more specific than metric, but in that system, the acceleration due to gravity is 9.8, the units being meters per second squared. Earlier when we were talking about the bullet, because he gave me the speed of the bullet, the nozzle speed, in feet per second, I gave the acceleration due to gravity in U.S. customary, which is 32 feet per second squared. In the SI unit, 9.8 meters per second squared. And folks, you can look it up. A meter is the ratio between those two is exactly the same ratio as how many feet are in a meter. If you do that, it's a little more than 3, okay? And 3 times 9.8 is a little more than 32, okay? So, square the time, here's your formula. D is the AT, 1/2 AT squared, so 1/2, 9.8, that's the acceleration due to gravity, times 3 seconds squared. Okay, I really dislike they don't put the units in here. 1/2 has no units, okay? 9.8 meters per second squared times 3 seconds squared. You square the unit as well as the numbers, that's 9 square seconds. The square seconds here cancels out there, and you're left with meters, of course. Okay? So the bottom line is, don't drop something from a very tall building, because by the time it reaches the ground, it's going at a very high rate of speed. And at a very high rate of speed, even a very light object can cause considerable damage to a car or to a person's head. Okay? I've heard it said before, but now I've heard someone say that Mythbusters disproved it, that if you dropped a penny from the top of the Empire State Building, you could actually cause someone to have a concussion if they happen to be walking by and land something. I don't know. I imagine that's pretty close to true, but part of it is penny might reach a terminal velocity and it may not be fast enough to do that much thing. It would hurt. It would definitely hurt. So, the distance fallen is proportional to the square of the time. Whereas, the distance back this up a little bit. The velocity is directly proportional to the time. Because velocity, V final is AT plus V initial. But if you dropped it from rest, then the initial velocity is 0. So this is a direct proportion. So in the first second, it falls 9.8 meters. Of 9.8 times 1. In the second, it's 9.8 times 2. Third, 9.8 times 3. Fourth, 9.8 times 4. So that same object is picking up equal speed every second, directly proportional to the time travel. Time travel. Okay? Still going at a pretty high rate of speed, when it reaches the ground. Okay? Make sense? All right. Now, in between those two, there's sort of a closer look, they call it. It's another blurb at the top of page 37. And I think we've even mentioned this before, and so I'll bring it up again. Because we always on the surface of the earth have air resistance. Okay? Therefore, I brought it up when I illustrated the Bernoulli effect. Okay? When you see these guys, say at the Tour de France or any of the other bicycle races, in the Olympics at races, speed skating, even runners, okay? At the racetrack, I mentioned this before. The big star on the team doesn't ever start out trying to take the lead and go on the whole race. If he does, he loses. Who Who leads? One of his lower teammates leads. Why? Because the star is going to draft on that guy. That's the term we usually use for it, because of air resistance. If you can get under let that first guy break the air resistance, then you can sort of drift along after him without having to expend as much energy. Now, I've never physically seen this happen, but I've seen pictures of it happen. How do the geese fly when they're migrating? In a V, is that what someone said? Yeah. Absolutely. Why do they do that? So they can draft off one another. And that one in front, after a while, he's going to pull out and go to the back, and someone else moves to the front. They know what they're doing, because he's going to get tired, or she, whichever one it is, and they're going to do that. And they continue doing that their whole life. Okay, they're pretty smart. Bird brain is a misnomer. Okay, they know what they're doing in those long, long trips. Okay, so the picture here is a bicycle racer's edge. Most of the time, and if you watch the long distance runs, I don't know what are they, 10Ks and things, whatever they are in the Olympics, long distance. Almost always they have some guy they call the pace setter. He gets out there, jumps to the lead, and starts running. He hardly ever, if ever, wins the race. Okay? Because he's having to overcome all that. And everybody else is sort of drafting on him. After a while, he's going to falter in someone else, and then the whole strategy of lag behind someone long enough, and then right at the end have enough energy to pass them and win. Okay? One notable exception to that, I don't know if y'all follow horse racing or not, and this was probably way before your time, but there was this one Triple Crown winner. Let me see if I can remember his name. Goodness gracious, it flew the coop. That horse was just incredible, because the Kentucky Derby was the first race. He jumped out in the lead, won it big time. Okay? And everybody said, oh, he's a sprinter. He's not going to have what it takes for, which is the second, Belmont Stakes or Preakness, I don't remember. Whichever one came next. Said he's not going to make it there. Dustin So's going to beat him there. Goodness, I wish I could remember his name. Well, Secretariat, you got it. Secretariat jumped to the lead in the, whatever the second race was, never gave up, won by a wider margin than he had in the Derby. They said, well, hang it up. The third one was the longest race. It was significantly longer. Said no horse can keep that kind of pace that long. He's going to fall apart. Dustin So's going to pass him big time. He jumped out to the lead and just kept running. And just kept widening the distance. He won the third one at a record margin. You know, a lot of times there are photo finishes. No. I mean, you had to turn off your camera and then pick it back up for the next horse. He was just an incredible runner. Powerful horse. Yeah, I believe it was Secretariat. Okay? So he broke this, but that's because he was just that strong of a horse. Okay. There's a closer look at the top of page 38 on free fall. Give it a shot. See what you think of it. It is pretty interesting. Kind of scary at that. Oh no, this isn't it. In an earlier edition, they talked about the person who had fallen the greatest distance without a parachute and survived. And fortunately, one of them that held the record for a while fell in a dense forest in the wintertime that had a lot of snow, and he fell an incredible distance. Either the parachute didn't function or the plane blew up and he didn't have a parachute. I don't know what the story was. That one came down with fairly minor injuries. But then somebody later, it seems like it may have been a woman, a plane blew up and she fell and survived, but very severely damaged. Lots of major injuries. Thought this was it, but it's not. They got a little kinder with their blurbs here. But they do have on page 38 two examples. Okay? No, one example. They just give two solutions to it. So let's do example 2.7. A rock that is dropped into a well hits the water in 3 seconds. Okay? So I'm not necessarily going to draw it. So let's just have the well here. It goes way down here. And somewhere down there is the water. You drop the rock from here, it falls, and it takes 3 seconds. T is equal to 3 seconds for it to fall. Okay? A rock that is dropped into a well hits the water in 3 seconds. Ignoring air resistance, how far is it to the water? So what was our formula? D is equal to 1/2 AT squared. And what do we use for A? Okay, if we're in the metric system or SI system, it's 1/2 9.8 meters per second squared. A number alone is no good without units, times 3 seconds squared. That would be, I'm just going to go on and take half of 9.8 so I don't have to carry it around. That's 4.9 meters per second times 9 seconds squared. You square the number, but you also square the units. Then the seconds squared cancel out, and you're left with 9 times 4.9 is 44.1 or something like that. What do they have? Yeah, they say 44 meters. I think it's 43 point. We'll round it to 44 meters because you only have. Well, I don't know why they round it, but yeah, I guess everything has 2 significant digits. No, the 3. Oh, they said 3.0. Okay, that's right. The time was 3.0 seconds, so we do have 2 significant digits. That would be 9.0. That's why they round to 2 digits. 44 meters. Okay? Now.
Excuse me, said
9.0. Because I didn't read the problem carefully. It's 3.0 seconds. When you square that, it's 9.0. So that's second squared. 9.0 seconds squared. And that's why it really comes out with, I think, 44.1 or something like that, if they round it. Does that make sense? Okay. All right. Now we're ready. I can tell we're ready, right? For compound motion. Now, what do you think we mean by compound motion? We were talking about horizontal motion initially. Then we talked about falling objects. That introduces the net force of gravity pulling it down. What do you reckon compound motion is? Well, right here. 3 types of motion. I would say number 1 is horizontal motion. That way it's the velocity, the action, unless it's acted on by an unbalanced force, is constant. Vertical motion, it's always being pulled down. If it's leaving from up here, it's increasing speed coming down. If you throw it up, then it's decreasing speed as it goes up. Well, what the compound motion is a combination of vertical and horizontal motion. Okay? Now, most of the time when we throw an object into the air, it's not straight up, though we could. That's perfectly fine. But if we throw it at any angle whatsoever other than 90 degrees, now you have horizontal motion at the same time you have gravity pulling down. Okay? Now here's your basic observation. Number one, gravity acts every bit of the flight. So you throw it up, gravity slowing down the vertical speed until at some point it stops vertically, and then on the way down, gravity is increasing the speed down. Okay? So gravity is acting at all times, every bit of that track. Okay? The acceleration, G, acceleration due to gravity, is independent of the object's motion. Whether you throw it up, you throw it down, you throw it horizontally, whatever you do to it, the acceleration due to gravity is constant. Completely independent of which way you threw it, how you threw it, how fast you threw it. Nothing depends on that. Okay? Now, there is one other that I'm surprised they didn't put here, but they must be going to do that on the next slide. So I'll give y'all a few minutes to get this one done. And that is the horizontal component. So let's think through this. When you throw an object at some angle, there is a vertical component to your motion. There's also a horizontal component. The greater the angle, the greater the vertical component, and the less the horizontal motion. The lower the angle, the less the vertical component, the greater the horizontal component. Okay? So, vectors are broken into components, horizontal, vertical, perpendicular to each other. Now, gravity acts to change vertical motion only. The horizontal component, gravity doesn't have any effect on it. Okay? We'll see that later in a later chapter 2. We'll hang on to that thought. So right now, it's the vertical component that gravity changes, because that's in the same direction as the gravitational force. By the way, what we're doing here, the compound motion, basically that's going to be what today's lab is dealing with. Okay, that's why I needed to get at least this far today, so we're going to be okay. We got this covered, so we can do the lab. Okay, everybody got it, or someone still writing? Okay. All right. So here are other characteristics of projectile motion. A perfectly vertical projectile going straight up. It slows down while it's going up. At some point, it stops because it's slowing down the whole way up. Some point it stops, and then after that, it accelerates downward. Well, guess what? It was accelerating downward when it was going up. It's accelerating downward when it was stopped. It's accelerating downward when it's on its way down. Okay, what they mean here is it's speeding up on its way down. The force of gravity acts downward throughout that motion. When the initial velocity is upward, it's slowing that velocity. When it finally gets to a stop, it starts pulling it down. It's always been pulling it down. Now the velocity increases as it goes down. Here's the other one, the horizontal projectile. Horizontal velocity remains the same throughout the motion, as long as you can neglect air resistance. Okay? Now, certainly, you fire it horizontally, gravity's going to pull it downward, but the horizontal component does not change because of gravity. Now, taken with the vertical motion, you get a curved path. You always have a curved path. Maybe it's not significantly curved, but it is always curved. Okay? That quarterback that tries to throw, what do they call it, a clothesline pass to his receiver, the receiver at best is going to be able to scoop it off the ground, or else it falls before it gets to him. You've got to get some arc to the ball, otherwise it's going to be too low for him to catch. You can't throw a perfectly horizontal ball. Gravity's always going to pull it down. Any of you baseball players or baseball fans? Anybody? No? Okay. What do you know about the pitcher's mound? Why do they call it a mound? It's elevated. It's higher. So the pitcher throws the ball. It may look like he's throwing it perfectly horizontal. He's not. He may be horizontal here, but it's going to move downward on its way there. Okay? And basically what a curved ball is one that's thrown more slowly, and then the curve, the arc. Now, it can have some sideways motion. We won't get into that, but it's arcing downward because it's not going as fast. Okay? Now, if anyone can explain a knuckleball, please do. Okay? Those are wacko. Okay? If you think back on my explanation of the rifling of a bullet that keeps it traveling in a more direct path, well, when you throw a baseball to get a direct path, same with a football. You throw the most effective football, it's always going to be a spiral, right? I've actually seen some punters that can kick an almost perfectly spiral ball. That's amazing. Those things can really go a long distance, okay? But if they're wobbling like this or like this, they're not going to go as far. Well, a baseball, when you throw it and get the spin on it, that might make it curve a little bit one way or another, but a knuckleball, they try to throw it with almost no spin at all. And now, whatever the air is doing to it, that's what makes it dance like crazy, and no one can predict where that ball's going to land up. And that's why hitters drive them crazy. They're used to hitting spinning balls, or trying to. A knuckleball will drive them crazy. Okay, that's beside the point here. So the horizontal projectiles always are going to be influenced by gravity, but it doesn't change the horizontal component of velocity. Changes the vertical component of velocity big time, but not the horizontal component. So if you take those together, it's always pulling down, but it's always keeps its horizontal component. That gives it a curved path. Okay? Now, every ball you throw is going to follow basically a parabolic path. Maybe a very shallow parabola, maybe a steep parabola. Okay? But it's going to be a parabolic path. Okay? Every basketball you ever shoot, with one exception, I've never done one in my life, and not likely ever to do one in my life, a dunk. That's just straight down. Okay? Not that. But every ball that you shoot otherwise is a parabola. A curved path. Okay? A golf ball follows a curved path. Everything follows these curved paths. That's because you have compound. Projectile motion is always compound motion, unless you fire it straight up. But straight out, it's going to be curved. All right. Now this is somewhat hard to believe. But if the gal here is firing an arrow perfectly horizontally, and the guy here is holding an arrow perfectly horizontally, and she releases the bow at the instant he drops it, those two arrows are going to hit the ground at the same time. Because the horizontal component of the velocity that she gives it, he's not giving any to it. That doesn't matter. That's constant for her, 0 for him. The vertical motion is identical. Okay? They will hit the ground at the same time. Okay? Because the vertical component is increasing on its way down at the same rate it is here. Horizontal component, it stays the same throughout her path. It shows about this little line up. See, that doesn't change. Vertical changes the same way his does. They hit the ground at the same time. Hard to believe, but absolutely true. Now, The rest of it we'll talk about in a later chapter. Okay. Oh, sorry. Okay, I got carried away. Oh, man. Sometimes I want to get carried away. Carried off somewhere. Okay. There have been a few people leaving. Do we need to take a break? Would that be worthwhile? Okay. So, after everybody gets this slide, whatever you're going to do with it, if you want to leave now, you can. Try to be back in less than 5 if you can. I'll wait until everybody gets this copy. I'll pause the recording so that there won't be a dead spot in it. You got it? All right, everybody got it? So I'll put a pause on it. Not tonight's lab. Tonight's lab's already all right. I did check with the biology instructor who sometimes has labs in the same lab we're going to be in tonight, but she's giving a test tonight, so there is no lab, so that gets us scot-free tonight, so there won't be any problem. But the next lab that we do, I usually like to use room 259 because that's where the setup is, and it's convenient to do in there, but she's going to be in class, so I'm going to have to find some other place to do the lab. I could probably use one of these 2 rooms, but the equipment is heavy. I don't want to move it up the stairs and then have to move it back down. So I have to figure something else out, but we'll manage that. But I checked with her and she said her class starts at 5:30 and goes till 6:45. So we can't wait till 6:45 to do the lab. That would be put us way too late. Though it's a very short lab, we could do that, but I don't want. You have 2 hours of lab time. I don't want to start it that late. So, well, I have to figure something else for that. So that's one reason I was delayed. Another was the student had an issue, so that was another thing. All right. We did this lab, and everybody got it covered. So let's move to the next one. Again, compound motion. Passing a football, as I've already mentioned, that's another example of compound motion. There is a weird-looking picture of a guy throwing a ball into the air and a kid up in a tree dropping a ball. If the guy threw it exactly the same height as his limb, and that's exactly where it stopped, and the kid, right at the moment that it stopped there, dropped the ball, they come down at exactly the same rate. So it's sort of the same type deal as we were just talking about. Here is the football thing. Okay. Now this goes for any of these objects, the balls, anything that you're doing. The quarterback, when he throws the football, as long as it's in his hand, he can exert a force on it, right? But the moment, the nanosecond that it leaves his hand, he's not got any more control over the ball. No more force from him. The ball is in motion there. No more force. The only force acting on that ball, once it leaves his touch, is the force due to gravity. There aren't any other forces. Yeah, it's got velocity, it's got all these things. There's no other force on it except gravity. So the vertical velocity begins decreasing at that instant. At some point up there, it actually stops, and then it starts increasing on the way back down. Okay? The horizontal motion is uniform throughout. Uniform here, 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 here. The horizontal motion is the same. The combination of the two, as I was saying, creates a parabola. Now, if you think about it, this goes for kicking footballs too. And if you ever think about it, very seldom is an extra point ever blocked, isn't it? Okay? But periodically they block field goals, right? Why do you reckon that's the case? Same kicker, same everything. Why do you reckon they can block field goals when they don't block extra points? Generally. I mean, I guess that some of them have been blocked, but not many. You know what I'm talking about? Well, guess what? The extra point is 3 yards from the goal line, okay? So then another 10 yards back there, 13 yards. That kicker can kick it just as high as he wants to, no, just about, and it's going to go through. I mean, if he has any motion this way. But a field goal from, say, 50 yards back or something like that, he can't kick it that far up because it's going to fall down right there. He's going to have to kick it at a lower angle, and at the lower angle, then the guys have a better chance of coming in and blocking, okay? Because there's no way he can kick it at a high angle from 50 yards back and even reach the goal line. Don't want to bring it up for those Tide fans, but remember there was a field goal attempt late in the season one year that went the other way and changed the ball game. Okay, but all the motion, however, the kicker, the thrower, the batter, the anything, they always travel in parabolic motion because there is a force downward. Okay, so here is the thing. No matter how much he tries to throw a bullet, he can't throw a bullet. It's always going to fall. So for a long pass downfield, there's going to be an arc. Okay. Now, there's sometimes that they arc the ball more close up too, and this goes for basketball as well. If the receiver is behind the defenders, you may want to put a little more arc to it so the defenders can't knock it down, but it still falls into the receiver's hand. Because the parabola, whatever you do here, is going to come pretty much in equal motion coming down. Throw the bullet, as much of the bullet as you can. Someone can get here and block the ball, or maybe intercept it. If it's really dropped from a high angle, that lessens the probability that's going to happen. All right, always follows the parabola. Notice again, when he throws here, the initial velocity upward is pretty steep. Horizontal is always constant. It's steep here, but less here, zero here. Now it's that much down here, more down here. So it's actually speeding up as the receiver goes to catch it. Okay. That pretty much finishes our discussion on compound motion. But as I mentioned here, golf balls, footballs, baseballs, volleyballs, you know, everything except the dunk and the basketball is going to be compound motion. Okay. Okay. So now we're going to look at what we call the 3 laws of motion. Now, the first of these laws, and by the way, the 3 laws were first detailed by Isaac Newton. Sir Isaac Newton, he later was known as. He lived from 1564 to 1642. AD, of course, you know, but that's, I'm not even sure Alabama was a territory then, okay? If it was anything, it was a territory. Georgia, I don't believe had even been founded then, okay? Massachusetts Bay Colony, maybe at the time of his death. So that was about the time they settled there. So he's way back there, folks. England, you know, Great Britain. He concurrently developed calculus and the law of gravitation and the 3 laws of motion. Everybody had been listening to Aristotle, who had lived so many, probably 300 or 400 years BC. Everybody was still following him until Galileo came along. Galileo died either 1563 or 64, right about the same time Newton was born, or a few months before, but within the same year. And Newton continued Galileo's work. In fact, the first of these 3 laws of motion was actually pretty much detailed by Galileo. Newton took it, expanded on it, and put them together with the other 2 to come up with the 3 laws of motion. But in order to do so, he had to develop a brand new mathematics, a brand new from-scratch mathematics, calculus, and the law of gravitation, and the law of light, okay, and it seems like there were a few others that he did. Amazing, the output of what one guy. The essential idea is forces, even though, I don't know what he actually wrote, because back then, all scientific writings were done in Latin. Okay, I don't read Latin. I don't understand Latin. I couldn't tell you what it was meaning. So all of his papers and titles and everything else were in Latin. So I don't know exactly if he ever used the term, whatever the Latin word for forces is, but that's the essential idea behind this work. Okay? So let's start with the first law of motion, Newton's first law of motion. Again, this was largely developed and stated by Galileo. Newton refined it and cleaned it up a little bit and then put it together with the other two. This is often called the law of inertia. Okay? Now again, can someone tell me what inertia means? What is inertia?
Momentum.
Second?
Momentum.
Okay, it sort of has to do a lot with momentum, and that's a nice concept to keep in mind. But inertia is the tendency of an object not to change its motion. Okay? If it's at rest, it tends to stay at rest. If it's moving, it tends to move in a straight line unless it's acted on by an unbalanced force that will keep. So that's exactly what it says here. Every object retains its state of rest or its state of uniform straight line motion unless it's acted on by unbalanced forces. So in the absence of unbalanced forces, every object maintains, and this is very similar to momentum, maintains its motion. If it's at rest, it maintains its rest. If it's moving, it tends not to change, not speed up, not slow down, not change direction. Straight line, uniform motion. Okay? And inertia resists any change in motion. Okay? Now, we got several examples of this that I'm certain y'all have experienced before in your life. Okay? Ever ridden either in a bus or in the back of a pickup truck and been standing there and someone accelerates? What do you tend to do? Fall. Okay? One way or another. If the bus is initially at rest, you're just standing there, you're in the back of a pickup, not a good thing to be standing in, but if you were, and then the truck starts, you tend to fall backwards. No. You're not falling backwards. You're trying to stay right where you were. The truck's moving out from under you. You feel like you're falling backward, but you're not. You're trying to stay right where you were, but the truck moves. So you get the sensation of falling back. And they actually says he falls back. He doesn't. He tries to stay right where he is. If he was on roller skates or ice skates or standing in an oil field, or something like that, it would move and he'd stay right there and he'd hit the back of the bus because the back of the bus would hit him. He wouldn't fall back. It would be the bus moves into his hill. That's inertia. Tends to stay right where you are. Okay? I can remember when my lawnmower died, I found a lawnmower repair shop not too far from where we lived, but it was a few miles. So I put the lawnmower in the back of the truck and tried to chock it so it wouldn't move. Didn't work too well. And every turn, every time I speeded up, it slowed down, bang, 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 turn. The lawnmower was trying to resist my change of motion, and it was banging the whole way there. It wasn't hurting anything, but it was annoying to me. Okay? Now, you probably also felt this. Been riding in a bus, standing there, you feel like you're okay, but then the bus turns. What do you feel like happens? You feel like you're thrown to the left. You're not thrown to the left. The bus is turning out from under you. You're trying to maintain your state of motion. The bus turns and you fall against the turning bus. Yeah, it feels like you're pushed outward to if the bus is turning to the right, you feel like you're thrown to the left. You're not. You're trying to stay right where you are. This cuts in front and pushes you this way. But it feels like you're thrown to the left. Okay? Your inertia is trying to keep you going in a straight line. Now, I can remember the guys with really hot cars back when I was in high school, they would claim they could put, I don't know what denomination it was, I'm going to say $10 bill because back then those were pretty valuable, but let's say $100 bill on the dash and say, okay, when I tell you, you try to get that $100 bill out, they're going to fix it to the dash. And then they accelerate real quickly, and you have to be awfully strong to be able to do. And while they're accelerating, they would claim you wouldn't be able to get that $100 bill. Now, of course, if it wasn't attached to the dash, it's going to fall backward too. But I never got the challenge. I think money grubbing enough, I would have got. No, I don't know. Okay, but that's Newton's first law of motion. All right. So again, in the absence of unbalanced forces, you're going to maintain your state of motion. If you're at rest, you tend to stay at rest. If you're moving, you want to keep moving straight line unless there's some unbalanced force that makes you change. Okay? Now the second law builds on that first. Okay? What if there is an unbalanced force? What does an unbalanced force do? It changes your motion. Now what term do we most associate with motion? There's lots of terms we associate with it. What one do we most associate with? Say again?
Speed.
Speed, exactly. Velocity. Okay? Now, what a force does is change your velocity. And what is a change of velocity?
Acceleration.
And acceleration. So forces cause accelerations. Okay? Now, we've knocked around a little bit at it, okay, but haven't actually gotten there. Now we're beginning to get more. We talked about displacements that are distances. We talked about time in seconds. We talked about distance per time with speed or velocity. Change of velocity is acceleration. Suddenly now we're getting to forces, and forces, the unit is a Newton. Okay? Now, going back to what we did in Chapter 1, forces are proportional to acceleration. Right? It's a proportionality. The greater the acceleration, the greater the force. The less the acceleration, the less the force. Negative acceleration is a negative force. Okay? Proportionality is there. To change that proportionality to an equation, what do we need? A proportionality constant. Some constant times that acceleration. And guess what that constant is? Your mass. So here is the Newton's equation that most is identified with the second law, F equal ma. Force is equal to mass times acceleration. Okay? The constant proportionality is the body's mass. And mass is associated with that inertia. The more the inertia, the more the tendency not to move, that means the body has more mass. Not to change directions. Okay, forces cause accelerations. Okay? The more force, the more acceleration. Direct proportionality. However, if you had a constant force, then you could divide one side or the other and say force divided by mass is equal to acceleration. Divide both sides by that, and guess what? Then acceleration is inversely proportional to the mass. Okay? And it is by means, even if you did it the other way, alpha over A is equal to M. Both of those are true, and so this is the one we normally would use. So accelerations are inversely proportional to the mass, so the more mass, the less the acceleration. Make sense? Okay. So those are the relationships we have. And it's all tied up in that one formula, force equal mass times acceleration. Now, I meant to say something back here on Newton's first law. I kind of doubt if Newton ever expressed it just that way. Because my understanding, again, I haven't read his work. I don't read Latin, so I don't know it. But from my understanding of what I've read about his work, Newton had this concept that he called quantity of motion. And that quantity of motion was the product of the mass times the velocity. Guess what mass times velocity is? You said it before, momentum. So he didn't, I don't think he used the term momentum. He called it the quantity of motion. It's mass times its velocity. Okay? It had both of those features in it, how much of the object was there and how fast it was going. And that's what he talked in terms of. So let's go back to that first law. Every object retains its state of motion, property of motion. Okay? That would be at rest. It would be zero. Mass times acceleration, velocity. Velocity is at rest. So its unit of motion would be zero. Okay? And it maintains that zero unless it's acted on by an unbalanced force. Whereas, if it's moving with a constant velocity, it maintains that property of motion, that state of motion, unless it's acted on by an unbalanced force. So it's a lot easier to say in terms of Newton's property of motion. It just is constant. It's zero or at some fixed value. It tends not to change. But then his second law would read something like this. If an object is acted on by an unbalanced force, it changes its state of motion, its property of motion. Okay? And later we'll see that means acceleration. Okay? In fact, I guess there's no reason not to do it now. A net force, and I'm going to call it N, L sub N, net force, changes the property of motion. So the mv that we call it, it changes that. So there's a delta from what it was to what it becomes. That's your change of motion. Well, the mass doesn't change, right? An object's mass is its object mass. So we can change this to net force is equal to mass times its change of velocity. And what is its rate of change of velocity? Acceleration. So that's where it comes from. Force equal mass times acceleration. We'll do this a little bit better in a later chapter. Okay? Now I think I need the space here to show the next thing coming. Oh, I meant to do this. Before we move, F equal MA. What's the SI unit for mass? Is that kilogram? Exactly. And what's kilogram? And what's the SI unit for an acceleration? Meters per second squared. Exactly. Meters per second would be a velocity. Meters per second squared would be an acceleration. Change of velocity per time. Okay? This is what we call a Newton, named after good old Sir Isaac. And I always thought that was not fair because I don't think he really focused that much on forces, but they named the force after him. I think they should have named the quantity of motion, mass times velocity, after him. But they didn't, and I have no right to say so. That's what a Newton is. A kilogram meter per second squared. Mass times an acceleration. Okay? Now, here's where we get into real big problems with the U.S. customary system. Remember what we said before? What's the unit of mass in the U.S. customary system? We really don't have one. We never talk about masses. There is a unit, but no one ever uses it. I told you what it was, right? Sounds like a slimy little pest in your garden. A slug. I didn't tell you all that? Or did I? Okay, I thought I had. Okay. Yes. So, a slug foot per second squared is technically a pound. Okay? But we never talk about slugs. Okay? So we just use the force of the unit of force, which is a pound. And don't even talk about masses. Nor do we talk much about the accelerations.
Excuse me. So it's kilograms and meters divided by seconds
Squared.
square?
Yeah, that is a Newton. Okay? You see, mass is measured in kilograms. Acceleration is measured in meters per second squared. Just like you did in lab. Remember?
So that means I have to divide it?
Yeah, mass per second squared. Remember in lab, you took the length of the track, right? That was in a length. We did it in centimeters, not meters, but that's centimeters. Then to get the speed, you divided by the time. That gave you centimeters per second. And then to get the acceleration, you divided that speed by time. And that gave you meter per second, which is meters per second squared. So that's your acceleration multiplied by the mass, kilogram. That gives you a meter.
So multiply by kilogram and divide by seconds
Squared.
square?
Okay, but this is 1 unit. Meters per second squared, that's your acceleration. And that is meters divided by a second. That gives you a velocity. And then that divided by a second, that's where the second squared comes in. Meters per second, and we call it meters per second squared, times a kilogram, that gives you a meter. So you treat the meters per second squared as a unit. You don't go around squaring seconds most of the time. It's just that you divide it by it twice, is what that means. Okay. Now, I'll erase this again. I did it once, but then I remembered I wanted to talk about the units. Okay. Now, there it is. Net force is mass times acceleration. Net force. That's not any individual force necessarily. That's a net force. The sum, the vector sum of all the forces acting on the object. Okay? And for instance, when we were cutting down the pine tree, Dan was pulling this way, I was pulling that way, so our net force between the two of us was this way, and then as my father-in-law cut the tree, gravity took over and pulled it the rest of the way down. That's why it landed in between us. Okay? Net force. Not any one force, but the net force is the object's mass times its acceleration. Okay? Now, sort of an example of this. Here I have a jet aircraft flying at 500 miles per hour, straight level flight. Okay? What's the net force on that plane? Plane flying 500 miles per hour, straight level flight. What's the net force acting on the plane? That's the speed. What's this net force? Is it accelerating? No. So if it's got no acceleration, the net force is 0. Anything going at constant speed, not changing direction, so constant velocity, the net force is 0. Okay. Does that mean there are no forces acting on the plane? No, that doesn't what it means. Certainly gravity is pulling down on that plane big time. But remember we talked about Bernoulli's force? Okay, that's the lift is pulling up on the plane. So the net force vertically is 0. That's why it's a straight level flight. Now, it's meeting lots of air resistance at 500 miles per hour, enormous amounts of air resistance. Now, that's why they make planes very streamlined, like this. But guess what? You got your engine firing like crazy out the back, and that's what overcomes that. The force in this direction is equal to the force in that direction. Net force is 0. Going at a constant speed, at very high speed, but unless it's accelerating, unless it's speeding up, or slowing down, or turning, the acceleration is 0. So the net force is 0. Individual forces, yeah, lots of them on the plane, but the net force would be 0. Okay? When you're in cruise, yes.
So if it increases the speed,
If what?
if it increases the
If
speed,
it increases speed, it accelerates. Exactly.
so it will have the net force.
If what?
If the speed is increased,
Yeah.
will it has the
That means you have a net force. If you're increasing, that means you've added more fuel out the back,
then
so you're
will it not air resistance also increase?
the what?
Air
resistance. If the air resistance suddenly decreased, yeah, then you would increase,
Yeah.
yeah, then you would slow down unless you gave it more
So
gas.
that will give.
Yeah.
That will.
That would be a
cause
negative
zero
acceleration. Yeah.
net force.
Second,
If the speed is increased,
right.
the air resistance is also increased, right?
Oh yeah, okay, I see what you're saying now. Yeah, if the speed increases, then that does. So unless you keep on the gas or accelerate. Same with the car. I mean, if you are at rest, of course, you don't have to provide any, but yeah, you move a little bit, you just have to keep your foot on the gas because it always air resistance. At a higher speed, you have to give it more to overcome the air resistance. Yeah. But if you're accelerating, then you have a net force that's not 0. Okay, but if you're at cruise control, you're still burning gas. You know, you're still pushing it forward, but that's because you're overcoming the air resistance. So if you're on cruise control, net force, unless you're turning direction, is 0. But when you accelerate, and guess what? Any of you ever go to, let's see, what's it called now? Splash Adventure, but one time it was called Alabama Adventure, and before that it was called Vision Land, and may have had a few other names in there. Did y'all ever go there? Okay. What was the most fun about the rides? Did you say it did have rides, didn't it? Okay. Was it the speed at which you rode? Or probably more so the change of speed? Because in a jet plane, 500 miles per hour, you walk around, you don't notice it. If you ever hit any air resistance, you know, it fall or you do anything else, or it speeds up suddenly or it slows down suddenly, and you're thrown around, that's what gets people excited. Now, on the roller coaster, it's not when you're traveling like this, it's when you're dipping or diving or loop-de-looping or changing direction. That's what gets people excited. It's that acceleration, the change of velocity, whether it's in direction or speed. That's what people pay for on the rides, not the speed at which you're traveling necessarily. Okay. Now, somewhere here, and they left it off, and I think it will show up somewhere later, but they have a guy riding a bicycle, okay? Pedaling the bicycle, he's exerting a force, and if he's traveling at a constant speed, he's exerting a force, but that's being countered by his air resistance, or whatever kind of resistance he has. As long as he's not changing speed, his net force is 0, okay? Now, if he is accelerating, he is exerting more force than what the opposing force is, so he's speeding up, or whatever. Now, if you plop his girlfriend, or her boyfriend, or some friend, onto the bicycle with the person, is he going to accelerate at the same rate, you think? No, if you increase the mass, acceleration goes down, right? Can't maintain that same unless you increase the force, okay? Especially if she's back there not pedaling any, then he's having to either work harder to keep the same acceleration, in other words, more force, or the acceleration decreases, okay, for the same force, because you doubled the mass, okay. All right. Before we move to the third law, then, Let's do example 2.8. This is on page 43. This is sort of talking about what we just did. A 60-kilogram bicycle. What does that measure? What does kilogram measure? Oh, bicycle and rider. What does that measure? Mass. 60 kilograms of mass. Yeah. You wouldn't have a 60-kilogram bicycle. If you did, bad choice of wheels. You know, you need to get something lighter than that. This is the mass of the bicycle and the riders. Okay? It accelerates, so that's your A, at 0.5 meters per second squared. Is that a good unit for an acceleration? Yes, distance per time per time. That is perfect. Okay? How much extra force was applied to make it accelerate? So in other words, what was the net force, the additional force that you had to supply? Pretty straightforward. What is net force? You've already forgotten. Say again? Say again? What is the net force? If you had a mass of 60 kilograms, acceleration of 0.5 meters per second squared, what's the net force to create that? Okay, yes. Net force is mass times acceleration, which would be 60 kilograms times 0.5 meters per second squared, and that would be, that's 1/2 of 60 is 30, what unit? Kilogram, meter per second squared, but that also has a name, Newton, 30 newtons. Exactly. Oh, and by the way, why do I capitalize the N, but I didn't capitalize the K or the M or the S? Name that for somebody. The units that are named after people, and sometimes titles, those are capitalized. Units that just derive themselves from somewhere else, they're not necessarily capitalized. Okay? Good deal. That was example 2.8, and that's exactly what they got in the book. Let's do 2.9. All right, to erase this? Everybody got it? What is the acceleration? This time we're looking for the acceleration. We don't know it. If a 20-kilogram cart, what is that a measure of? 20 kilograms?
Yes.
That's the mass, okay? Of a 20-kilogram cart, if the net force on it is 40 newtons. So what's its acceleration? How would you do that? Say that again.
F or N.
Okay. Oh, F over M, is that what you... Yeah, okay. Now, if you start with your basic, net force is equal to mass times acceleration, and now we're looking for acceleration, divide both sides by mass. Okay? Masses go out here, and you have acceleration is equal to net force over mass. Now, if you like the triangles or circles, do you like those better? Anybody? You use those as a tool to do the calculation? No? Or yes? You know what I'm talking about?
Yeah.
Yeah. Do you use them or not? Okay. If you did, here's how you set up the triangle. Okay, that's the dividing line. There's the multiplication line. Since your original formula is net force equal mass times acceleration, you put the net force here, then mass times acceleration there. So if you're looking for acceleration, cover the acceleration, you have net force divided by mass, exactly like we had here. And in this problem, that was 40 newtons divided by 20 kilograms. That was the 20 kilograms. Now that doesn't look right, does it? Newtons per kilogram. That's not very good. Here's what you do. Break the newtons down into its basic units. What are the basic units for Newton? kilogram meter per second squared divided by 20 kilograms. The kilograms go out, and sure enough, and you can divide this, you get 2. Do they say 2.0 or just 2? They just say 2. 2 meters per second squared, which is a great unit for acceleration, meters per second squared. So you see, units are your friends. They will help keep you on track. If the units balance out, there's a good chance you did the problem right. Okay? Good deal. Any questions? Now, they have a little concepts applied second law experiment. That's sort of interesting. I've actually heard of an experiment that would be, I think, more fun to do. And it's sort of involved, but we could do it, especially if it had a nice level parking lot and plenty of room to move around. What you would do, and I've actually heard this described this way, you get 2 or 3 people on the back of a car, not on the back, but at the back of a car, pushing against scales, regular scales that you would use in the bathroom, you know, to weigh yourself, okay? Pushing against those. Have someone sitting in the car, the door open, and with a stopwatch, and every time a second passes by, you put a little cone out there, you know, or maybe shoot a paint bottle gun or something, just to mark where you are every second, okay? And people are pushing on the car, and you try to keep that at a constant thing, say 20 pounds. 40 pounds, 80 pounds, whatever, pushing with some constant thing, 2 or 3 people across there pushing with the same amount. So you have your net force acting on it, what your push is, and you have the put out the cones or squirt the paint gun or whatever you're doing, and then later go back and measure how you're accelerating and see what you get. It would be a fun experiment to do. The trouble is we don't have that many parking lots that are all that flat. And we have enough people driving around, it might not be safe to do that. But it would still be, oh, by the way, you put the car in neutral, okay, and take the brake off, you know, that would be fun to do too. Okay. Now, but anyway, they're pretty similar to their second law experiment. All right, before we move too far with this, okay, so here, now they finally get around to doing. Still talk about Newton's second law. The more mass, the less acceleration. We said that before, because mass and acceleration are inversely proportional to each other. Okay? The focus here is on the net force. If the net force is 0, that means the air resistance, tire friction, and all that kind of stuff have to exactly match the force that's being applied. The result is no acceleration, constant velocity, 0 change of velocity, so net acceleration 0. Now, here's the deal. Here's the guy on the bicycle, okay? He's pedaling along, and what we know, he's going at a constant speed. And if we know he's going at a constant speed, does that mean he's coasting? I think not. If he's coasting, the odds are he's losing speed. Because he still has, especially if he's sitting up like that, he's got a lot of air resistance. So if he's pedaling at a constant speed, then his applied force that he's pushing the tire against the road equals to the frictional force both of the road and air resistance. And it depends on how fast he's going, which of those is greater. At a slow speed, the friction resistance probably is more than the air resistance. But if he's going at a large speed, the friction resistance may be the same. The air resistance would be greater. He'd have to be doing a larger applied force. But if the net force is 0, and I do not like the way they've written this, it seems like to me this should say net, shouldn't say applied. Here's the applied force. There's the applied force. If these two add to 0, that's your net force. So I think they have labeled this poorly. Let me see if I can find that in the book. Yes, in the book, that is not applied, that is net. If the net force is 0, then that tells me several things. He's at a constant speed. Whatever that speed is, 3 miles per hour, 7 miles per hour, 20 miles per hour, 0 miles per hour. If the net force is 0, then he's at a constant speed. 0 acceleration. He's not turning, because it's not just speed, it's velocity. Okay? No acceleration, constant velocity. Okay? So it has to be straight line motion. So they had that labeled badly. That should be net force is 0. All right, now a little bit of a timeout here. Okay? Remember, in this formula, that is never some specific force. That's your net force. The vector sum of all the forces acting on the body, that determines the body's acceleration. Whatever the body's mass is, times that acceleration, that gives the net force acting. But the form here is what we're interested in. Force is mass times acceleration. Now, when we're talking about weight, weight is usually not a net force. That's one of the component forces. But the form is just like this. Weight is mass times one acceleration. What acceleration is that? The acceleration due to gravity, which in the SI unit is 9.8 meters per second squared. If you were in the U.S. customary system, that would be the force due to gravity would be 32 feet per second squared. But in SI units, 9.8 meters per second squared. But the key here, weight is an A force. It's not a net force, but it's a force. The mass is the mass, okay? And the acceleration due to gravity is a specific acceleration. Whether you're accelerating or not, that's the acceleration due to gravity. This is your specific acceleration, the whole object's acceleration. The key here is not to think of these as the same equations, but they have the same forms. So this is measured in newtons, just like that is. That's measured in kilograms, just like that. This is measured in meters per second squared, just like acceleration. Okay? So weight is the force due to gravity. Now I'm teaching another physics course on Wednesday evenings to a group of students who are going into the sonography program. And their text doesn't use this for weight, they use F sub W, force due to weight. And that may be a better terminology, but it's just more writing. I like little w to be weight. Okay. Now, with that in mind, your mass is your mass. The quantitative measure of the amount of inertia, the amount of matter there is, whatever you want to call that, that's your mass. How much of the object substance is there? The weight is not how much of the substance there, it's the force of gravity acting on that mass. Okay? Now, let's say, and by the way, and this guy's actually been here, there's a guy lives in the area here named Larry DeLucas. Does that name ring a bell to anybody? He was a professor at UAB. He's now no longer at UAB, but he's working independently. I can't remember what area he was in, crystallography or something. And he was a good scientist, is a good scientist, and he proposed an experiment that would be neat to do on one of the shuttle missions. NASA reviewed a whole bunch of these and selected his, and he was willing to. They trained him. He got to go into outer space and do his experiment in microgravity, almost no gravity. Okay? Now, when he was down here on Earth, he had a certain mass and he had a certain weight. I'm just going to guess maybe 160, 170 pounds, something like that. Just looking at him, I'd say maybe 180, I don't know. Okay? Now, when he went up into space, did his mass change? Probably not. I mean, he's the same person, okay? Did his weight change?
Yes.
Big time! Because now he was no longer at this acceleration due to gravity. When you get far enough above the Earth, yeah, the acceleration due to gravity falls off as 1 over r squared, or the distance squared. So yeah, his weight changed. He became almost weightless out there in space, but his mass stayed the same. So don't confuse mass with weight. On the surface of the Earth, they differ only by a constant that's multiplied, so they're equivalent. They're proportional to each other. When you get outside the Earth's gravitational field, no, weight changes a big number. On the moon, seems like one of the astronauts took his golf clubs and golf balls with him and hit a golf ball on the moon. Record length of a golf ball, okay? Because of very little gravity there, that thing took off. I don't think he ever retrieved the ball, okay? So, what we measure force in, newtons in the SI units, pounds in the U.S. customary unit. Mass, kilograms in the SI units, we really don't ever measure mass in the U.S. customary system. And that's why, because they only differ by a constant, it doesn't vary. That's why in the grocery store, if you ever go to the scales to weigh your veggies or whatever you're going to be buying there, oranges, fruit, whatever it is, you put them in. One side of the scale is going to be in pounds and ounces. The other one is going to be in kilograms. They're not even measuring the same thing. On the surface of the Earth, they're proportional to each other, but really they should be either in newtons and pounds or kilograms and slugs. But how many grocery stores are going to sell 7 slugs of oranges? Ew, it just doesn't even sound right. So they don't do it. They do kilograms and pounds. Okay? They're measuring different things. So. All right. Now we get to Newton's. Wait. There is one more example. Yeah, I don't have any white space. There we go. So let's get rid of my writing here. Let's do example 210. Okay. Wait a minute. Have you let me go over? Did we? What time is it? 5:45. Look at that. You're going to let me just keep on talking. We'll begin next time with example 210. The only reason I noticed that's where we stopped last time I taught the course. I said, is it time to stop? Sure enough, it is. Okay. I know we took a break a little bit earlier, but it's going to take a little bit of time to set up the lab. Not much. But I've got to get all my stuff shut down here and stuff carried down. So if you want to take a little break, do so. This time, when you go down the hall here, don't go in the lab to the right, 253. Go across the hall here to 252. Okay? Don't mess with anything. There's a lot of glass in there that belongs to the biology and chemistry field. Don't mess with it. We don't want any broken glass. And I have setups in there. They're set up the way we need to start, so don't mess with anything. Why don't you take a break and leave the lab alone until I get there. Or if you go in there, just don't mess with it. I don't want to have to set it up again. Okay, I'm going to put a pause. Okay, we're ready to do lab, 3, isn't it? Okay. This lab is on projectile motion, which is what we were talking about in class today, at least the last part, or middle part. And as discussed in class, there's 3 kinds of motion, basically. Horizontal motion, vertical motion, and then compound motion. We're talking about projectile motion, which is compound motion, and that's what the lab's going to be today. Now, probably not quite like you think, but it's going to be a form of projectile motion. Now, what you see the setups are here, and hopefully nobody's touched anything too badly. Okay, let's see if they're pretty. Yep, someone's touched something. Someone else. See, that one looks pretty good. Okay. All right, we got our setups here. Please don't mess with them. We're going to be doing the same thing several times on these. Okay? There are several formulas. One particularly on page 66, delta y is equal to 1/2 gt sub y squared. We're going to be using that one later. And then we have dx is equal to delta x over delta t. Certainly you're going to be doing that pretty soon. Then you got another couple we're going to be dealing with. Now at some point, because I can't get the board in here, I can't get it in here, but they got writing on it. So I'm going to have to set up an equation for you. I'm going to have to go either to that classroom or our classroom. So we'll probably go back to the classroom for just a short period to do one equation for you. But anyway, we'll get there in just a minute. Now our procedure, I'm going to modify this procedure ever so slightly. Okay? And I'll tell you what those modifications are when it gets time. So we're doing something like on page 67. It says adjust the ramp. Do not adjust the ramp. Okay? I'll tell you what we're going to do instead, and it makes it a lot easier, and you don't have the ramp adjusted. Okay? So leave the ramp alone. It's set up just like you'll need it. Okay? Now, what I've got set up, just so everybody can see, and by the way, we do need to distribute a little bit. Oh, I forgot the power roll. I meant to do that before I turn on the projector. I mean the sound. So I'm going to pause the sound again. Don't let me... Okay. Now, what we're going to do next, and I've set it up for you very easily, let me start back up. What we're going to do is you're going to take this meter stick. Oh, here's what I thought of the roll. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. 5 per team, with one team having 6. So this team can have 6. That means, what is it, 3 out of you? 1, 2, 3, 4, 6. Okay, 1, 2, 3, 4, 5, 6, 7. One of you come down to, you have 6 here. One of you. One of each of you, each team come down and join this team. Okay, you stay where you are. You're fine. Okay, one each from each of these 2 teams move over to this team. Anybody? I just need a body to move here. Help me. Okay, the longer it takes, the longer we'll be here. Okay, thank you. Okay, now I'm going to show you on this one. Don't mess with anything either one. Notice the ramp here. There's the ramp, but our path here is going to go here, and I've measured it out, so that's exactly 1 meter. Which is how many centimeters? 100 centimeters. So our path here is 100 centimeters. So it says measure. Okay, wait. Okay, sorry. It says adjust the ramp, blah, blah, blah. Measure the horizontal part of the ramp labeled BC. And if you see the picture here, that's the horizontal part here. That's where the meter stick is. That is 100 centimeters. Everybody, okay? Now what you'll do is release the ball. Now, where's the ball? You'll see a cup up on near you, a cup, and you got the ball. Good. What you'll do is take the meter stick, move over here to the ramp until you measure 10 centimeters from the tabletop. Okay? And at that point, you can hold it however you want to here. When you're at 10 centimeters, that's where you'll release the ball, and then you let it roll, and it goes on down. Okay? Got it? Okay. That's all right. Okay. No, don't do it yet. So that's how you do your runs. Okay? You'll do 3 runs. Okay? This won't be an exact one. You'll also find up here on the top shelf your stopwatches. See them? Okay. So let's say, this won't be the right one. So let's say here, start, stop, okay? That was 1.53 seconds. That was nowhere close to what any of your measurements would be. So that's what you're doing. You're measuring the time from it hits the table here, you'll hear it, until it rolls off the table and stop it. So the person who's doing the stopwatch, be so you can see when it starts, when it stops, and then reset.
It starts from here?
From where it touches here. Not from up there, but when it touches the tabletop. You're only measuring the time of the horizontal run, not the slanted run. You understand? Okay. You'll make at least 3 runs. The reason it says at least is if one of them is way out from the other 2, then repeat that one. Okay, so at least 3 runs, and you'll find the average velocity. This time, unlike what we did before, this time, did I turn on my projector? Yeah, okay. Okay, what we did before, we threw out high and low. This time we'll average your velocities. You'll do a velocity for each run. Okay? There's your stopwatch, by the way. Sorry about that. You said, yeah. Okay. Now, record your data in table 6.1. That's over here on page 70. And that's going to be the 10 centimeter above the tabletop. So your first 3 runs will be from the same place, 10 centimeters from the tabletop. Release the ball from there. Start the stopwatch when it touches the table. End it when it rolls off. Got it? Everybody understand? Okay, y'all divide up however you want to do. Who's going to be doing what? Someone's going to be holding the meter stick. Someone's going to be releasing the ball. Someone's going to be using the stopwatch. And someone's going to be recording data. So you do it however you need to do. Go to it. Any questions? You're going to move that out of the way because you need the path to be clear. But you will need to know where your 10 centimeters is. So you do need the meter stick to measure your 10 centimeters up. And you be sure you start the ball from the same position every time. I'm sorry?
These 3 are 10 centimeters.
Those are the 3 problems. But you do it from 10 centimeters. Like I showed you, you got it. You do this at 10 centimeters, and that's where you release the ball from. 3 times. And if one of them's way off, repeat that. Okay? And probably every team will need a ball catcher. Okay? All right. All right. If and when you have a question, please ask. I hope every team has at least one calculator, right?
Okay, so
Someone fails his ball catcher. Okay. 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 You know 3 runs each at the same height, 10 centimeters? Are y'all doing that?
Yeah.
Okay.
Everybody
Second.
He said we're only making
Okay, don't worry about that. Oh, you've already done? And they all came out.
It's the table when it falls off.
Oh,
It's when it falls off.
drop it from 10 centimeters.
Okay. All right. Okay.
Start. The ball is here. Start the
That's why
here.
circles do when it fell.
Okay.
Don't push it right.
Y'all have to do it. Okay. Huh? Right. Yeah, that's what ultimately I do the nearest tip from the
When
center.
it hits the table, right?
Okay.
What?
Okay.
Drop it from 10 cents. 10.
What's that?
Drop it from 10.
Yeah, release it. That's when you start. And then it falls off the second spot. You sure you're at this?
Yeah, that's right.
That's how I write it down. You don't get that. Everybody report that. That's time. What y'all get for your 10 cents? Approximately your time. Have you done one yet?
We've done 3. I don't have any.
Okay, yeah. What were your numbers? Big enough?
This is 100% right here.
Now, you see the delta y? Here's what I was going to show you. Delta y is just from the core to the top. That's delta y. That's why you did that. Did you measure that?
Yeah.
Okay. All right. Now, y'all, unfortunately, are going to have to wait just a minute to go late up. But they're not far behind. They've done 3. I got the pencils in the classroom. If anyone wants to pick up the pencil when we go there. Don't have many, but I have a few. Y'all done 3 runs? Okay. Have all teams got your average? Okay. You got your distance from the floor. Did y'all measure that? Distance from the floor to the tabletop? Okay, that's what we're vertical. Here's 10th of a centimeter. Did y'all do that? I wish I could bring the board in here, but it's got writing on it, and I don't want to have to do it right. Okay. Have all the teams measured this from before? He's up there. He's not bothering anybody. I'm ready for you, man.
Vertical distance is 10, right?
What's that?
Vertical distance 10 centimeters.
No. If you look at one graph, the vertical distance is from the floor to the tabletop. Right? You come down here and measure floor to tabletop. So there's a 10th of a centimeter. Floor to the tabletop, there's a 10th of a centimeter. I would measure with the other side. Wouldn't you? Okay. Okay, whatever. Nearest 10th of a centimeter. Okay, nearest 10th of a centimeter. Okay, everybody got all the measurements made for the first run. Okay, let's go back. Let's go back to the classroom because I need to do an analysis for you. And that means I have to take my computer too. So, okay, on the bottom of page 66, you see a bunch of formulas there, that last paragraph. And they go through some calculations. I'm not going to derive those, but you see 2 here, delta y is equal blah, 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 and delta y is equal to something else. It's just a very simple difference they have there. Okay? Now, if you turn to page 67, on number 2, that's the next page, on number 2, here's what it says. It says solve delta y. I don't know why it does that kind of mess. Okay. There's something. This is why it's doing it. Okay. All right. That may be better. Okay. All right. Says here, solve this. Delta y, that's your change of y, that's what you measured at the end, floor to the tabletop. Delta y is equal to 1/2 times g. You know what g is, right? Say again? Okay, we'll get that in a second. Delta x squared over v sub x squared. Okay? Now what they say is to solve this for delta x. So we want to solve for this one. Okay? What would you say the first thing we need to do, or one thing we need to do? To solve for delta x. In other words, isolate that delta x. What would we do? Second? No, let's not put in the numbers. Let's solve for delta x.
Yeah.
How do we do that? Isolate the delta x. What would be your first step? Or a step? Anybody?
Divide.
Second? What are you subtracting? No, it's not being added to anything, so you can't subtract something that's not added. All these things are multiplied or divided. So how do we solve for delta x?
Divide.
By what? Huh?
Delta x.
Second?
Delta x.
Okay. I want delta x in the numerator. I don't want it in the denominator. So let's not do that. No, it's already there. It's in the numerator. I need to get everything else on the other side. How do we do that? Anybody?
Subtract.
There's nothing added, so we don't subtract. What operations do you see here? Second?
Division.
I see division. What do you see divided?
V.
The 2 and the v sub x squared, right?
Yeah.
So how do we undo the division? Multiply. So let's multiply both sides of the equation by 2v sub x squared. 2v sub x squared. The 2 will go out with that. The v sub x squared goes out there. Now we have, I'll write this again. I'm going to switch sides if that's okay. What we have left on the right, I'm going to write on the left. G times delta x squared is equal to 2v sub x squared delta y. Got it?
Yeah.
Okay. I still want to get delta x isolated. So what do we?
By G.
Divide by g. Okay? Divide by g. Good. Now we're rid of that one. We almost have delta x isolated. We have delta x squared isolated. How do you undo that?
Square root.
Take the square root. So take the square root of both sides, and that will give us delta x is equal to, now you can either take the square root of v squared and pull it on the outside, or you leave it in. Which you prefer? Say again? Say again?
I don't know.
How would you want to do it? I don't care.
Yeah.
Leave it inside or take it out? Leave it in. Okay, that would be the square root of 2v sub x squared delta y over g. Now, what we don't know is this. We know everything in here. We know 2, right? That's 2. V sub x, what was that? Didn't y'all each calculate it? Okay, so you have your v sub x. You're going to have to square it. The delta y, didn't y'all measure that?
Yeah.
Okay. Now, what was your v sub x measured in? I just want the units, not the numbers.
And centimeter per square.
Centimeters per second. And then you're going to square it, right? Okay, the delta y was measured in?
Centimeters.
Centimeters. What is g measured in?
Meters per second.
Ooh, problem there, folks. That's measured in meters. These are both measured in centimeters, and this will be measured in centimeters. So we've got to get that g, which is normally what? Someone said it earlier. 9.8 meters per second squared. How many centimeters in a meter? 100. So how many would be 9.8 meters?
98.
98?
No, 980.
980. That would be 980 centimeters per second squared. So when you fill in the numbers, be sure you put that in for your G. Yes?
So can the Vx square divide like both cancels out with the square root?
That's what I asked earlier, if you wanted to pull the V sub x out, and y'all said leave it in. You can do it either way, okay? If you want to pull the V sub x out, it would just be a V sub x here without the square, and then don't put it in here. So either way you want to do it. That's why I asked, y'all said leave it in.
Can we like cancel out the square root and the square?
That's what I just said. If you pull that out, that would be what it is. V sub x on the outside, square root of 2 times delta y divided by this g on the inside.
No, I'm trying to cancel out the square root. Can we do that or not?
The only way to undo a square root is to square everything. And that's where we came from. We had it squared, I mean, delta x squared. If we cancel out the square root, as you're saying, that means squaring it. That makes it delta x squared again. We don't want that. We want delta x. Now, you can pull out the v sub x squared out of the square root. You don't want to do that. Well, then, don't do it. Oh, sorry. Wrong thing. Okay. Hit the wrong key. Sorry. So, let's not do this. Okay. All right. So you got your numbers, do the calculation, and tell me approximately what you get as a delta x. Every team will have a different answer. Now, if one team has several different answers, you got a problem, but we'll work on that. So tell me what some of the delta x's are. Be sure you use that as your G. So while we're in here at the comfort of our room, and does anyone need a pencil? I have like 3 pencils up here. If someone wants a pencil, someone said you didn't have a pencil before. I have this other one, but I can't seem to make the lead come out, so I don't know what's going on with it. It must be broken out of lead or something. So anyone need a pencil? Okay. I'll let you choose which direction you want. Okay, your choice. Anyone need a pencil? Anyone else need a pencil? Okay, when you get your delta x, someone call it out just so I'll see what kind of ballpark we got. Okay, I'm going to make up some numbers just to show you how this works. Whoops. Okay. Let's just say 2 is 2. I'll use that one. V sub x. I'm going to say 0.9. I doubt if that's going to be anyone's V sub x. 0.9 centimeters per second. I'm going to square that. The delta y, I'm going to say is 90 centimeters. I know that's not what anybody's is. And then G is, I'll use that one, 980 centimeters per second squared. Okay? So I'm going to do the math here. The square root of 2 times. Now when you square 0.9, that comes out 0.81. That's why I chose that, because it'd be easy. Centimeters squared per second squared. You square the units as well as the number. Okay? Then multiply that times 90 centimeters. Now these are not the right numbers, by the way, and divide it by 980 centimeters per second squared. Now the reason I'm doing this is to show you what the units come out as. Okay? Here you have per second squared, there you have per second squared. Those disappear. Here you have a centimeter, there you have a centimeter. Those disappear. What you wind up with centimeters squared under the square root, that becomes centimeters. So that's what your delta x is going to be. You figure out what the number is. Okay? And I don't have a calculator, so I can't do this. But if you multiply these things out, this is going to be 180. And these are not the numbers you should use. Times 481, so that's going to be about, say, 170 or something like that. Divided by this, yeah. Oh, I didn't square that. Yeah, I did. Okay, sorry about that.
Excuse me, so that's for number 2 in page 67?
Say again?
Is that for question 2 or page 67?
On 67, number 2 and 67, it says record what delta x, okay, use a data table to find delta x. Now I've used made up numbers. Obviously this number is too small, that number is too small, so yeah, mine isn't going to be anywhere close. You tell me what you get yours to be. Just call out some calculation of delta x. Just so I know about what it is. Anybody?
43.
43? Okay, that sounds reasonable. Centimeters. Anybody else get a number?
40.46.
Okay, that sounds reasonable. Any others? Is everybody getting a number somewhere around there? You use your data. Don't use my data. Okay, I just made these up. You use the 2 and use the 980, but that's all you use from this. Everybody get a number somewhere on the order of 30 to 40 to 50, something like that? Let me know, yes or no?
Yes.
Yes?
Yes.
Okay? Do I have a yes on every team? I heard 2 numbers, I didn't hear the third team. Did we lose a whole team?
53.
Huh?
53.
Second?
53.
53. Okay, they all sound pretty reasonable. Okay? So I'm going to shut this down, okay? And we're going to go back to the lab. But remember how you did that, because you're going to do it for the next 2 as well. Okay? So I'm going to put this on pause.